Good afternoon, everyone. It's Pi Day, March 14th, 2022. That's the only math joke I'm going to make today. This is the only time I've even referenced it today. Previously, when we were doing our review for the midterm, we started looking at chapter 4, and I want to go over a little bit of it again real quick before we dive into 4. Remember, we were looking at data points and how if they're grouped together in a pattern, what's going on? Why is that moving on its own? If they're grouped together, like where they could like make a line, if they were all a little bit more consolidated, we call that a correlation. Whether it's going upwards like this line is, or downwards like this line is. And we call what we measure the correlation by R. So we use the letter R for the correlation, and it's got an ugly formula, and we're not going to use it. We do have other forms of correlation, but we're looking at linear correlation where it makes a straight line. And two major things we'll use is stats, summary stats correlation, and stats regression simple linear. That's in our StatCrunch. And in each case, it's going to give us an R somewhere. The stats regression gives us a little bit more. It gives us that line of best fit we were talking about. And we'll walk over problems using it. R had some properties. It's always between -1 and 1. The closer it is to +1, the more perfect positive correlation it has. The closer it is to -1, the more perfect negative correlation it has. Well, -1 and +1 are perfect, but then less than those is a better correlation. And when R is near 0, it doesn't show evidence of linear correlation at all, but there may be other forms. And it is impacted by outliers. When we do use it, we're going to use R. When we get calculated, we're going to compare it to a critical values table. So maybe I should open that up right now and get that available for us. COS. I'll have this open on another tab. I gotta log in. I'm gonna go into Canvas. And we'll go into our course. I have 3 stats courses that I'm teaching. It's in files, and then it's under useful handouts and statistics. And it's that stats, formulas, and tables. And I'll scroll down to it. It's on page 5, I believe, 5 or 6. There it is. The critical values for correlation coefficient is table 2. This is the one we're going to look at when we use it in a little bit. When we're going to look at R, compare it to that, and make a decision about whether it's got a correlation or not. And many of the homework problems, as you'll see when you're doing chapter 4, give you that link to the table. But if they don't, it's in files and handout. And then we had all of our review for the midterm. I will be, for the midterm, going through and checking for rounding errors over the next couple days and rewarding partial credit where appropriate. So your scores will go, if they could go up. I won't say they will go up, because maybe you just either did fantastic and they can't go up, or you didn't make any mistakes that are entry mistakes. But it could go up, and you'll be able to see your midterm score before the 18th on my math lab. I will update the value, and then you'll know how you did. So I want to do draw, and this is where we're going to continue today. I don't want pencil, I want pen. So 3/14/2022 is called Pi Day, like that kind of pie. It's for all the science and math and engineering nerds. Pi is approximately 3.14, and thus the 3 and the 1/4. That's where they get it from, in case you wanted to know. For this, we're going to take a look at an actual value, or an example that we're going to do. So the example I'm going to go into StatCrunch right now. Or let's see, where is this? I'm going to view the data sets from our textbook and see if it has a link to it. I want to look at chapter 4, and it's 427 that I'm looking for, that I wanted to use as a teaching example. So this is, we looked at it, saw it before. This says total lengths, and this says weights. And I'll just switch back over to the writing screen so you can see what I'm about to say. So 4.2.7 is our example. And it gives us the total length in centimeters is 1 column. And the other column is total weight in kilograms. And what you don't know is this is about bears. These are bears. So they measured, they captured a bear or tranquilized it, measured it, weighed it, released it back into captivity. We want to see if there's a correlation. What's going on here? Is there a correlation between length and weight? Of bears? And that's a question, so I'll put a question mark on it. Now for that, I want to remind you that we need to find two things. We need to find R, and we need the critical value. This is from StatCrunch, and this is from table 2 in that handout. And maybe I'll list the values, that might help. So we got length, weight. Let's see, I'm going to break it in sets of, I know how many bears there were. There was 12. So I'll make, I want to undo that last one. Make that line a little bit longer. And now I'll go in and start entering them. Let's see, does my book have, my notes have the same values that are in StatCrunch? So let me check real quick. Yes, so I'll leave that up there so you can see that. Let's see if I can make that bigger. While I'm copying that over to my table and my notes, just so you can start writing it directly from there. So let's see, 90, 60, 85, 100. And then my bottom 6. And I see there are 12 rows. That's kind of handy. That's our sample size. So n equals 12 is our sample size. And we're going to need that for our critical value table. I'll give you another 30 seconds to copy down the table if you're copying it down. All right, I'm going to take a look at the data. Let me zoom back out a little bit. Let's just see what the graph looks like. Let's do a scatter plot on it. We want to see if the length of the bear makes the weight change. So I'm going to say X is my length and my response variable will be my weight. And we're just going to display points. That should be good as it is. And remember, it made this line like this. Is there any other options in this? No. So we can see that it looks a little all over the place. We do have a low weight one with a low length and a high length one with a high weight. And the rest are kind of in the middle. I don't like that the graph shows that it starts at 120 and 160. That's a pretty bad design. Is there a way to change that? No. So that's the scatter plot. We can also look at we're going to do stats, regression, simple linear. We're going to choose the same thing. Length is the X variable and Y variable would be weight. And we're not doing any hypothesis tests. We're just going to click compute. And we get this information. And there's a lot of stuff going on. If I click over to this real quick, we can see they plot the data and they do a best fit line. This fitted line here correlates with this equation right here. So we need this R correlation value. So I'm going to write that down in my notes real quick. 0.703900318. And while I'm there, I'm going to write down that equation again. Remember, weight was our Y value, so I'm not going to write weight, I'm going to write Y. And I'll do negative 142 point, I'll do 2 decimal places right here, plus 1.69, and then total length was our X value. So I'll do that. So I borrowed some stuff from this. I'm gonna switch back over to the writing screen where you can see what I'm doing. You can see what I put there. I got my R value right there. Quit doing that, it's annoying. The Y value is listed like this right here. I'm gonna rearrange it and put the X value first, the way we normally write equations. And so this is kind of like in mx plus b form, which we'll use. We talked about before. M is slope and b is the y-intercept. I went too far off the screen. I now need to hop over and look at the critical value table, and I need n equals 12. That's pretty important. So I'm going to come over here and I'm going to look for critical value. and n equals 12 is 0.576. Can I zoom in there at all? There we go. So 12, n equals 12 gives me a critical value of 0.576. I'll go back to the writing. And then what we do is we compare the absolute value of R with the critical value. The absolute value is just make it positive. Since my critical value is in 3 decimal places, I'll just do 3 decimal places for my R. And if I were to do that, it would be 0.704. And of those two, the R value is bigger. Since this is the case, when the absolute value of R is greater than critical value, there is linear correlation. And the fact that R was initially positive, R equals 0.703 is positive, it means there's positive linear correlation. Pause and let that sink in for a second. Okay. I'm going to go back over to the StatCrunch picture. Where'd it go? So there it is. I want to look at that graph again, and I want to explain to you how they're picking this line. They're like, how do you get this line and not some other line? So what they do is they can make an equation that does it, but what this really does is it's going through and finding the vertical, like up and down distance from each point to a line, to the line. And what they do is they square it, they square that distance, and then they add them up. And so like this has got a short distance between these two right here. This point's a long ways away from it. So it's got a bigger distance, and when you square it's even bigger. This one's also a long ways, but several of them are close. And so what they do is they find that distance. So find the line. They use math to do it. We're going to have the computer do it. But what is the line? What makes it the best fit line? Is this. It squares all the vertical distances from the points to the line. And sums them up. This vertical distance maybe I should give you more information. The vertical distance is, we're going to call y hat. It's the, well, no, sorry. Let's identify the stuff. Y hat is going to be the predicted value of Y based on the line. And then we're just going to use regular Y for an actual bear's value, a particular bear's value. They call it the residual. The residual is Y minus Y hat. Another way of thinking it rather than those is the observed bears minus the predicted bears. So, and this is that vertical distance. The residual is that vertical distance. And I told you they take each one and they square it, and then they add them up. So this is like the sum of squares. Let me change how I put this. And this is the sum of squares. I'm going to leave a little room because I'm going to add something to it. And then the line that is the line we use, we want to minimize this, find the value that's the smallest. And so what they call this is the sum of least squares. It's the lowest. So sometimes you'll see in StatCrunch, it will say SSE. I'll go back and see if it shows it on our residual table. This is the sum of squared errors. That error is another word for residual, because it's how far off, how much error the line was from the actual bear. So on our bear line, the bear line gave us Y equaled 1.69x plus, oops, not plus, minus 142.471. Where they come up with these values, I told you they did some math. I'll just tell you what the math is, just so you know what the computer's doing. This is in the form of B1x plus B0. That's what they use in the stupid stats book. I think they should have just used mx plus b. But this is our m and this is our b. B1 is the R value times the standard deviation of the Y values over the standard deviation of the X values. And B0 is the Y-intercept. 1 second. I'll make this short. All right, back to where we were. Oh, no, cans don't. And meeting, shrink that. There we go. So a couple things to point out. We already showed that there was positive linear correlation. Let's look at that value from that data. I'm going to draw the graph over here, but I want to look at it again. So the lowest value, I'm going to like try to sketch this over here on my screen while I'm looking at this, but I'm going to include all the space that they don't show. So I'm going to try to start my Y values at 6 or 0 and my X values at 0 as well. So this goes 60 up to like, maybe I need to change that. 60 is maybe right there. And 150, let's see, 30, 60, 90, 120, 150. And let's see, the X values go from 120 to like 170. So maybe I'll do every 50 here on my X values. And I got 60 and 120 there. And the biggest X value is at 166. And its height is about 140 there. So we'll go up to about 140. Yeah, all right. And this was the best fit line that they had. So this was my, I wanted to continue. This was my 1.69x minus 142.47. And we can see if I extend that line downward, if I just make the blue line go, that looks like crap. If I just keep having the blue line go downward, this is my Y-intercept. That's the negative 142.47. And that looks like really big text when I zoom back in. So I'm going to rewrite that smaller. So we have a couple of things to think about. When we're given this best fit line, first off, we want to look at two things. How do we interpret B, or how do we interpret this and this? And we're going to talk about that right here. I need more room to write. Well, that 1.69, is that the value? 1.69 was my M, or they called it B1. This was my slope. If X increases by 1, let me change color. I got a lot of blue here. So the interpretation is if X increases by 1, that average increase in Y is the M or B1. That's very similar to the way we described M normally. If X increased by 1, Y increased by M. But now, since the line doesn't actually match the actual data points, it's just the best fit, we say it's the average increase. So the weight of the bear on average goes up by 1.7 kilograms for every centimeter of the bear. Average weight of bears. Of this size. This is pretty important for what I'm adding that in because it's going to be part of what we say next. The average weight of bears of this size goes up by 1.69 kilograms for every centimeter of the bear. And now we want to talk about that y-intercept. The y-intercept, or the B0, was negative 142.47, was it? 47. And the way we want to look at this is we want to look at a couple things. First off, are there any values of X close to 0? In this case, there's not, but I want to give you the other thing we look for in case there is. B. Does it make sense to have X equals 0? If either one of these is not true, we don't want to interpret the y-intercept. Because it's not applicable to the situation. It's not applicable to the problem. And let's take a look at how that relates to our bears. Our bears, our X was our length, and our Y values were our weights. Does a bear of 0 length make sense? No. Even if you try to argue embryo or, going down as far as you can go, it still has a size. It may be a minuscule size, but it's not 0. So a length of 0 doesn't make any sense. And therefore finding the weight of it doesn't make any sense, because bears of 0 length don't exist. Another way of looking at it is, does a negative weight make sense? Again, no. So where does this line actually, what values can we actually use? Like 50 centimeter bear, 100 centimeter bear. 100 centimeter bear is 1 meter. 1 meter is about 2.7 feet. It sounds like a bear cub, right? The bear cubs can't be that big. What does this thing predict for bears of 100 centimeters? What does the line predict for bears of 100 centimeters? So I'm going to put the line down again. It was 1.69x minus 142.47. When you're, this line is the prediction line or best fit line. If you want to predict a value, just plug it in. Y equals 1.69 times that 100 minus 142.47. And that's about 26.5 kilograms. What about like 100? Let's not go 50 centimeter bear. That's like one foot. Let's change it. Let's look at like 75. About a 75 centimeter bear. 75 centimeter bear is, I don't know, a little over 2 feet, 2+ feet, not much bigger than 2 feet. I plug those in and I see what I get. I don't know if 26.5 kilograms is reasonable. I don't. I have no idea. But I know that negative 15.72 kilograms is not. So, is 100 good? I don't know. What we got to look at is the range of the values of the bears. What was our input values on the bears? And I'm going to come back over to StatCrunch and look at the data that we have. I'll pause for a second, let you guys write if you're writing. All right, I'll come over and look at the bears. If I look over here, 120.5 was the smallest length. I'm gonna write these down on my screen while I'm talking. Smallest length was 120.5. And that value, my zooms in the way. That's 166. This is an easier way to look than looking at all the data. Put your cursor over the dot. 166 is the length, and 120.5 is the length. Like, it's not that bad when there's only 12 entries, but if there's, 1,000 entries, oh, hell no, you don't want to go through the list looking for the biggest and smallest. So I got those. I'm going to come over here and I'm not going to do the full scale, like 2-dimensional graph. Let's just do a number line. This equation predicts values in this region. Because it doesn't have data outside it. Now, you might be able to extend it maybe a little bit in either direction. But we saw that going over to 75 was bad. 100 might be bad. So you don't want to use it to predict values that are outside the range too much. I want to say there was, I don't have it with me. I'm going to have to look it up. Mark Twain had noted it at one point. The length of the Mississippi River changes over time. It used to meander more, and it slowly gets straighter and straighter. I don't know why, just the way the evolution of the planet. It slowly gets straighter and straighter, but they measured how much, how much the length of the Mississippi had changed over 100 years. And he had noticed that if that rate continued, the length of the Mississippi would reduce to 0 in 200 years. He noticed that there was some flaws in that logic of trying to extrapolate beyond the means of what the data represents. And that's similar here. Clearly, a 75 centimeter bear, we cannot have negative 15.72 weight. So it doesn't make sense. Other types of questions you will see in this stuff. Ooh, what's green look like? Let's come over and change one of the other ones. I'm going to try green. Maybe I need to make it wider. Oh, that's not bad. I like it. You guys, is that okay? It looks good on my screen. I don't know how it comes through on yours. Let's see. I see a chat response. That's good. All right. Thanks, Gabe. So types of questions you'll see. Obviously, I'm going to use the bear data, but this extends to other types of problems that you'll see in them. If we find 160 centimeter bear weighing 139 kilograms, is the bear heavier or lighter than the average bear? maybe I should say in this length range. If we had more than 12 bears worth of data, we might be able to answer for all bears. But we're just going to go for this data range right here. So what we want to do is we want to find the predicted weight. Of a bear that is 160 centimeters. And then we will compare our bear to it. This predicted value bear, this is where X equals 160 on that best fit line. And rather than just eyeballing it, we can calculate it. It's a pretty easy calculation. We had the equation was 1.69x minus 142.47. We'll just stick in 160. This becomes calculator work. I should say 160. And I'm getting 127.93 kilograms. So if I do a little like simulation of that line, the predicted value of a bear of 160 centimeters right there would be 127.93 kilograms. Now, visually, I can picture this because the values go up as we go up. So our bear, the bear we're looking at, had 139 kilograms, which is a little bit above it, which means he's heavier. But you don't need to draw the picture and do all that to determine it. We can just do that residual thing. It was the observed minus predicted. $139 minus, I'll round that to 128, is 11. If the residual is greater than 0, it's larger. And if it's less than 0, it's smaller. In the terms of what we're looking at with the bears, larger means heavier, and smaller means lighter, weighs less. And 11 is greater than 0. That's a heavier bear. Okay. A little bit more to do today, but we're going to be done pretty soon. We're going to look at, we're jumping to back to chapter 7 or forward to chapter 7. This was chapter 7.3. It was not on your midterm, even though it's in chapter 7, because it required this line stuff, and the line's a little complicated. And this was on normal distributions. Chapter 7 was normal stuff. So we're going to come back there. And we're going to note a couple things. When they do a normal probability plot, the observed values are the x-axis. Or the horizontal left-right values. And when we were doing chapter 7.2, we shifted to z-scores. And so they use z-scores for the y-axis or vertical, which is up or down. So I'm going to load up another data set, see what we can see from it. See if I should have looked at this before I started. I'm going to load 7.3.4 data set. Quit moving. Oh, my wrist keeps getting, that's what's going on. My wrist keeps getting close to it. Okay. I'm going to come back over here. This was, if you're here and you click on view the data sets from your textbook, that's what I'm doing. And I'm looking for chapter 7. And I want to use 7.3, number 4. And this is on chocolate chips in a bag. Chocolate chips per bag. And I'm going to scroll down to just see how many rows there are. There are 40 rows. And so in this sample, N is 40. Now notice I only have one column. Okay. So only one column. When you have data like this, what you want to do, if you have only one column, oh, back over to my writing. So I wrote down the chocolate chips per bag is N equals 40, and we have only one column. And I want to note, if you have only one column, like this, if it's z-scores, which ours isn't, you want to do stats, regression, simple linear. That doesn't seem right. Is that even doable? No, it's something else. Is it QQ plot? It's QQ plot. No, that's the observed value. I'm going to have to come back to you with the z-scores. Something's wrong here. I'll get back to you. If it's observed values like we have here, here we do the QQ plot. So, and when you do the QQ plot, you want to add correlation stats. You'll see it as an option. We'll go back and look at it. And you want to do normal quantiles on the y-axis. Okay, let's take a look at that real quick. We're going to do graphs, QQ plot. I'm going to say chips per bag. And I'm going to add the correlation statistic and then click on normal quantiles on y-axis. And we click compute. And I'm going to write it down before I shift back to the other screen. My correlation stat. My correlation value is 0.986. We've got n equals 40. I think we can see pretty damn well that this has got a good linear correlation. You know, you can eyeball on the bears, we couldn't eyeball. But this, we can eyeball it pretty well. And look how big that correlation statistic is, 0.986. But if we couldn't eyeball it well, we can always look at that critical value table. So I'm going to come back over to it and look at it. And the critical value table only went up to 30. So we'll just use that. So my critical value for n equals 30, that's the best we got, is 0.361. That's what I'm writing down. That's what I wrote down. And clearly, when we compare R and CV, 0.986 is a lot bigger than 0.361. So there is positive linear correlation. And since there is positive normal or positive linear correlation, what we're doing in 7.3 is we have this data set. We don't know how it's distributed. We don't know if it's actually normally distributed or not. And we want it to be normally distributed for everything we do in statistics later on. So since there is correlation, the data is approximately normally distributed. We can do that QQ plot on the bears too. We did it on the chocolate chips. Let's go and look at those bears again. Let's do the QQ plot there. Does doing them each separately do anything? And we see the lengths and the weights follow roughly a straight line. They each have their own correlation statistic, but we can see they each follow along that. Now, I know in my notes over here, it's not in this one. It's in this one. This has got all the StatCrunch tech help. I'm thinking maybe if I look at chapter 7.3, I can go find what it's supposed to be. Because I told you the wrong thing a second ago. Let's just come down to chapter 7. Well, I guess it's just QQ plot the whole way. Why do I have something different in my notes? Oh, that makes sense. Value that's been converted to a z-score is still has the same relationship among all of them. This is always handy. If you're looking for something, come look for it in here. Like if we look in chapter 4, was it? We didn't do contingency tables. 4.3, we didn't go over this. It goes more into doing the residuals and stuff like that. But I had told you could do stats, summary stats, and correlation. And I also told you could do stats, regression, simple linear. So if like you missed something, you can always come back here and look. And I think that's going to be it for today. Do you guys have any questions? That's it for the new content. We're going to do 8.1 and 8.2 on Wednesday, and then we should be back up to speed. We'll be all caught up. If you don't have any questions, I will see you guys on Wednesday. Stopping the recording.